Okay, this is a new concept called scalar product. Very new, okay? Scalar product. Let's start with the definition. As with all definition, you don't question the definition. I will explain the workings later, but we do not question the definition of a scalar product. All right? So the definition goes like this. If I take any two vectors like that, two vectors, if I dot to any two vectors, the definition is such that it is the magnitude of A times the magnitude of B multiplied by the cosine of the angle between the two vectors here. So again, I say there's no questioning. It is a definition. If you like, you can have you can define this on your own as, I don't know, mod A mod B cube, whatever. You can define this, but it has no use whatsoever. All right, mathematicians before that have realized that if we define it like that, called a scalar product, there is some use to it. That's it. So I want to emphasize it is a definition. There's nothing to question. Now, if I have two vectors A and B, a very useful thing about this definition is this. If I have two vectors, if theta happen to be 90 degrees, all right, if theta happen to be 90 degrees, which means A and B are perpendicular, then surely cosine 90 is 0. Right? Surely cosine 90 is 0, which means A dot B is equals to 0. This is the part that I talk about being useful. Okay? If I define it cosine theta, if theta happen to be 90 degrees, means they're perpendicular, means A dot B is 0. So this relationship, we will make use of it time and time again. All right? So now that we've dealt with the definition, let's take a look at some properties. Firstly, because of the definition, if you see on the bottom right here, because of this definition here, then A dot B at the end is a number. It's a real number. It's not a vector. Why? Because obviously mod A is a number, magnitude of B is a number, cosine theta is a number. It's a real number. Sometimes we say it's a scalar. It is not a vector. Okay, so bear in mind it is a scalar or real number. It's not a vector. Next. Scalar product is commutative. I don't think it's difficult to understand because if you take a look at, if I define, since you define it like that, if you see this here, all right, since you define it like that, then it's easy to tell me that B dot A is modulus of B, modulus of A, cosine theta, and this theta remains the same, and this multiplication is commutative. So it's not difficult to understand. The next two may not be very obvious, but I will show it first, then I'll explain a little bit. It is distributive over addition and subtraction. So it's a distributive law of scalar product over addition and subtraction. Bear in mind this is scalar product. It's not multiplication like real number. A is a vector, B is a vector, C is a vector. You do not take this for granted. But I can show it, that's not a problem. The proof may not be very simple, but accept it. If you don't want to see the proof, accept it. But don't treat it as a real number. Okay, the distributive law. Next, if I take two vectors in column vector, I dot each other like that, it can be shown that if I dot it, okay, I use an example here. That means this. It can be shown that if I take 1, 2, 3, dot 4, 5, 6, it can be shown it is actually 1 times 4 plus 2 times 5 plus 3 times 6. Again, I don't want to take this for granted. It can really be shown very mathematically. The proof is not super easy, neither is it super difficult. But if you don't want to see the proof, sure, you can skip the following slides. All right, we will prove it later in the next video. That's that.